Good morning, everybody. I'm Zhixin and from Institute of Geography, Chinese Academy of Sciences. I'm going to talk about hydroclimate variations of the past 1,000 years over Eastern China. First, I would like to talk historical archives over China, which I used in my study. So during the past 2,000 years, China experienced many dynasties. So many historical book records have been kept during the past 2,000 years, which related with like wet or dry information, or cold or warm information, and social impact. But based on the recording format, there are different between the dynasty. Like before 1470, we have historian book, like 24 historians. This is the next dynasty write down something for the previous dynasty. Also, we have personal diaries and notes. From 1471 to 1911, we have local gazettes. It also the same information with 24 historians, but by recorded by county, by each county. And also from 1736 to 1911, we have memos of emperor, which recorded rainfall and snowfall depths. This is a measurement very systematically. I will show you later. Because the political center, so most of records, especially on Eastern China, and the temperature is very discontinuous. So before 960, very few records were available, and 961 to 1470, some of records are available and better than the previous, but still it's not very plenty of them. If I show the percentage to show how many records what we have, it should be in these periods maybe 30% we have the records, and these periods we have like 60% records, and after 1470 100% we have. So during the past 40 years, my colleagues collect the different records for the historical records, like the historian and the local gazettes. This is an example, and this one is a personal diaries. So different with other historical document. The handwriting didn't change a lot during the whole historical time, so it is easy to recognize for them. And the meaning didn't change too much, so it is easy for understanding to us. This one is the memos to emperor. So most of the records over the Eastern China, and this is an example. They are writing by the officers in the Qing dynasty, and the red color was written by emperor. In order to convert the rainfall depths into the rainfall amount, we did many experiments following the methods in ancient time, in ancient people. Based on above historical documents, a data set of the drought and the flood index was reconstructed with a normal distribution. So this data set has 5 grade category from 1 to 5. It means from dry to flat. Here is an example how many sets we have. It's 33 sets. So I already said since many records were missing. So before 1470, we only have 25 data available, but after that, 100% are available. So we already use this data set to analyze the hydroclimate variation with 3 regions in China. And also we did the spatial precipitation spatial pattern at different cold or warm periods. And here I will show you the 3 main points. The first one, we use new documents found recently to improve the quality and the complexity and what statistic methods we used. And the second one, to analyze the hydroclimate variation over Eastern China during the past millennium, including temporal, spatial pattern, and extreme events. The third one, we detect the possible linkage with climate forcings. So we with more and more digitized the historical document, so we can update and reconstruct like 10% dry or wet data set. In order to interpolate the missing value, we use a factor and clustering and analysis methods. So this is a map. We divide the Eastern China into 9 sub-regions. So the columns are the monthly precipitation. Then we use probability regression to interpolate within the region spatially, and use a Markov chain based on the known rules from 1471 to 2000 in the time series. After that, we improve the missing value from 75 improve to the 35 missing value. So you can see this, the blue line already get upper. And the most missing data were in southeast and southwest. So we do the regional interpolation based on the multivariable linear regression. And then we get 7 regions hydroclimate data set. So this is a time series. Then we move the results and the discussions. After we doing the wavelet and the EEMD signal extractions, the common cycles were detected, like 30 years, 70 to 80 years, 100 to 120 years, and 250 years. So here is a 30 years cycle. From correlation coefficients matrix, you can see they are all consistent phase. But on this time scale, you can see the some reverse pattern here. You can see the north part and the south part, they are opposite with a special pattern. Like this map, you will see here is dry and here is wet, so completely opposite. Also on the 100 years cycle, you can see in the North China and the Yangtze River southeast, they also have this opposite pattern like here. It's the Yangtze River and the southwest, southeast. Here it's wet and here it's dry. Also, we detect the extreme events and the stage. If we use like 60 stations were in dry condition, then we consider as the extreme drought event. Then we can have 91 years extreme drought events and 76 years with extreme flood events. So more extreme drought events occurred in 11th century, 15th century to 16th century, and the 20th century. And more extreme flood events occurred 18th century to 19th century. So the 17th century, both extreme flood and extreme drought events occurred. Here I show some examples for the extreme drought and extreme flood event spatially, how they distribute. Also, we compare with Ed Cook's work. Here is Ed Cook's results. Here is our results. You can see from 1638 to 1641, this is his result, but for us it's a little bit different. Although they are all drought, but you know the like southeast is completely different with this figure. And also the other years. And another one from 1876 to 1878, the same thing. It's, you know, you can see the large areas were in dry condition, but here not a lot, only in North China this year's. So I think maybe the problem is in these results only one proxy data available, but in our results we have 63 stations proxy data available, so it's quite different. Also, we detect the PDO, the relationship with our results. So you can see the north before 1350 to 1450, you can see the PDO and our precipitation have positive relationship, but after that it's reverse. But in south it's different. Before this time they are negative, and after that they are positive. Also, we compare with SST positive anomaly in the equatorial, central, and the eastern Pacific from the global SST. We think maybe this is a trigger to the extreme droughts in North China. Then we make a main conclusion quickly. The first hydroclimate variation over Eastern China showed 30 years, 70 to 80 years, and 100 years, or 2 and 50-year cycles. And the spatial pattern of drought in north and flood in south can be detected during the past 1,000 years. And more drought and flood extreme events both occurred in 17th century. And the PDO and positive SST anomalies could have possible link with drought and flood spatial patterns. Thank you.
Thank you for that. It was fantastic. Just a very quick question about the comparisons between your data set and the dendro tree ring data set. Have you done much? Have you actually tried to look at correlations between your stations plus locations where the tree ring network actually has data points? I was quite interested. I see there's big differences, but I was interested if you correlated at those places to see if there's variability.
Since you know in China only the train ring station, most of them lies in the western China, but only 1 or 2 stations in eastern China. So usually we cannot compare them.
Okay, good morning, everyone. So in this study, we try to look at the European hydrological response to volcanic eruption using the tree-ring-based proxy of the last millennium. And this is work done by my student Yuzhen Gao and myself. So just a little bit of background. The large explosive volcanic eruptions, they will emit significant amount of sulfate aerosol into the stratosphere, and they will turn into sulfate aerosol and cool the surface by reflecting the sunlight. So this cooling effect is evidenced over the last century on the global average temperatures you can see on the left figure here. The cooling will suppress evaporation and monsoon circulations by reduce the land-sea thermal contrast, so which has potential to impact the hydrological cycles. And this hydrological influence is observed after the 1991 Pinatubo eruption. As shown on this right panel here, we see a global scale precipitation and runoff reductions. And this is also observed in the model simulations. So in this 2013 study by Eilers et al., they used the Hadley CM3 model to look at the hydrological, actually global precipitation response after the 18 tropical eruptions of the last millennium. And what they see is there's a significant global precipitation reduction for most of these tropical eruptions. Then if you compare the model simulation with the observations for the 5 eruptions of the last century, we can see is while there is a very good agreement on the tropical and the southern hemisphere, the comparison in the extratropical northern hemisphere is kind of noisy. For example, in Europe, we see there in the models they indicate they see a wetland response in Central Europe and also in Mediterranean areas, while observations show a dry tendency in these two regions. Versus in Northern Europe, the models see drying response, and the observations show wetland response. And in a follow-up study, these patterns emerges when you compare the observation and the CMIP5 model simulations. And this is the case also for China, Eastern China, and the Eastern United States as well. So the question remains, which is right, the model or the observation? And that brings up the first question that we want to address. What does proxy show? Because proxy has a longer time period, show about the volcanic hydro response in Europe over this last millennium and what causes this response. On the other hand, because the hydrological systems, they will evolve under warming conditions. So this is a very recent evaluation of this hydrological response under global warming, recent warming. And what they found is a lot of these climatically humid areas like part of the Mediterranean areas, for example, are getting drier under this global warming. So the second question that we want to ask is, does the responses of volcanic sulfate aerosol counteract or intensify this hydrological impact of recent anthropogenic warming? And we think this has implications when we evaluate what the hydrological system will behave when a future big eruption occur, or when the stratospheric geoengineering by injecting sulfate aerosol into the stratosphere was proposed as an emergency response to climate emergency. So to address these two questions, we used the tree-ring-based Old World Drought Atlas by Cook et al. As our hydrological index, and we remove the potential ENSO influence by regressing out, by using a cold town index to regress out any ENSO-related moisture anomalies. And then we use recently updated the ice core-based volcanic index by Michael Seigel et al. And to develop our key event year list. And then for each category of these volcanic events, we conduct a superposed epoch analysis to maximize the signal versus noise ratio. And then we run a Monte Carlo significance test for this composite results. Then after that, we do a spatial and temporal analysis. So just a briefing on the data set. On the top panel shows this volcanic histories over the last millennia. We see there is a significant number of eruptions occurring in this period. And there are a number of them. A number of these events are larger than the 1991 Pinatubo eruption, which I showed on the first slides. So in order to evaluate the impact of magnitude in the response, we divided the tropical eruption into those bigger than Pinatubo eruption and those smaller than Pinatubo eruptions. So finally, we have 3 event lists. We have 17 smaller than Pinatubo tropical eruptions, 15 larger than Pinatubo eruptions, and 44 middle to high latitude northern hemisphere eruptions. And here is our hydrological data set, the ODA. ODA is the latest family of the Northern Hemisphere Drought Atlas, and it is compiled using over 100 live cheering record evenly distributed around this area, combined with the fossil cheering record, historical record, and archaeological record. And it is calibrated with the June, July, August PDSI. So it's a reflection of the late spring and the summer soil moisture. So here are our results. On average, we see there's overall wetting response on the year and 1 year after the tropical eruptions. And followed by a wetting tendency 2 years after the eruption. And this significant hydrological response is mainly caused by the larger than Pinatubo eruptions, as you can see by this red curve on the right panel here. So this indicates that for tropical eruption to have a significant hydrological impact in European, it has to be, it's probably needed to be bigger than the Pinatubo eruption in 1991. Especially, we see that the wetting response is mainly centered in northeast Europe and Mediterranean area or South Europe. And the drying response starting in year 2 after eruption is mainly centered in the Central Europe and also England irises. So we arbitrarily divide this area into 5 regions. The South Europe, mainly the Mediterranean region, the West Central Europe, East Central Europe, West North Europe, and East North Europe. And we do a regional average superposed epoch analysis. And here's the result. So in general, we see the wetting of the year and 1 year after eruption is mainly centered in Southern Europe and Northeast Europe, while the drying at year 2 and some regions, year 3, is centered in Northwest Europe and also West Central Europe. And a little bit on the East Central Europe as well on the second year of the eruption. So our result from this proxy record agrees well with regional climate model simulation focused on this region using, I think it's ACAM5 simulations. So we think that the mechanisms that they found in their model simulation can help us to explain the patterns we see in the proxy data set. And so in their studies, they found that these volcanic radiated perturbations, they weaken the South African monsoon and Asian monsoon. So the weakened African monsoon suppressed the subsidence over the Mediterranean region through a weakened Hadley cell. So a weakened Mediterranean pressure gradients. And this is what you can see here on the left panel for the 500 millibar geopotential and also the upward and the velocity, the vertical velocity here. And the weakened Asian monsoon reduced the Isthmian, which then promotes the cloud formation and the convection in the eastern Mediterranean area, which causes more precipitation over there. And secondly, the volcanic-induced cooling can lead to a negative summer NAO, which causes a southward shift of this storm track. And this giant, that explains the giant tendency over the central and the North Europe, and also the wetland response in the southern Europe. But this part, especially whether it's, the southward shift of the storm track is caused by a positive summer NAO, it's actually a negative east Antarctica pattern is still on debate. So we needed to look into this in more detail in future studies. For the northern hemisphere mid to high latitude eruptions, we don't see a significant hydrological response if all the 44 eruptions are taken into consideration. But if we only take the largest 14 eruptions with global volcanic forcing larger than 1.5 watt per square meter, we do see a drying or droughting happening 2 years after the eruption. And especially on the right panel shows the response to the northern hemisphere eruption, and on the right is the figure you've seen before for the tropical eruptions. Okay. So we see that there's actually an overall drying tendency in the region when we compare to the tropical ones. But the significant drying is happening in the Central Europe and the England isles. So and it agrees well with what we see for the tropical eruption at this year. So we think that some of the mechanisms causing the hydrological tendency for the tropical eruptions may help to explaining this response after tropical eruptions as well. So just to wrap up, we think we find the answers to the two questions that we want to address. So proxy results generally agree with the observations of the last century, and it suggests that eruptions of pinatubo size or larger are needed to cause significant hydro response in Europe. And secondly, the hydrological influence of this stratospheric sulfate aerosol on the regional scale are complex and may depend strongly on the large scale circulation, especially the teleconnections. And secondly, the volcanic perturbation is likely to alleviate the drying condition we see now in the Mediterranean under global warming, but it also can intensify the wetting tendency in the Northern Europe region. And these results highlight the diverse and potentially adverse hydrological effect if we are to propose injecting this sulfate aerosol into the stratosphere as an emergency response. So with that, I would like to finish my presentation. Thanks.
Good morning to everyone. I would like to present here some results of our research group dealing with the Little Ice Age climate, and we are a group of people from Masaryk University, Brno, Czech Republic, and I would like to acknowledge my colleagues and also historians who are cooperating with us. For sure you know something about Little Ice Age. In literature you can find a lot of definitions from point of view of temporal definition, but here I will follow this period from 1550 to 1850 according to these studies, and this period is nicely covered our data which we elaborated, and this period also nicely fit with some proxies. Here is an example of glaciers from Alpine region, and also some forcing factors. Here we can find very nicely two periods of Maunder and Dalton minimum solar activities. For this period, we were able in last decades to collect several different temperature sensitive and precipitation sensitive proxies, and they were collected not only for point of view this proxy data, but they were also used for some reconstruction. The problem is that these series differ. They differ as for the proxy type, sampling region, sensitivity to different variables, seasonality. And our aim of this study was to do some synthesis. It means to put them together and try to find something which is characterizing this little ice age climate, but not only the little ice age climate, because as you can see, it was not homogeneous period, but to define something which is called little ice age type of climate, so some periods that are really typical for this period. The methodology was relatively simple. We put all this existing data together using principal component analysis, and the new variables, principal components, were used to calibrate to instrumental data for temperature and for precipitation. Calibrated series were verified statistically, or also not only formally, but with some other existing data, and we tried to detect some little ice age type of events, as I mentioned. And finally, we compared these results with the existing proxy reconstruction in broader scale in Central Europe. Here are the proxies that were used for the temperature reconstruction. At first, we used these indices of air temperature derived from different documentary series, not only from Czech lands, but also from neighboring countries from the Central Europe. Unfortunately, we have this information only up to the middle of the 19th century. Then we use two phenological-like proxies, winter wheat harvest dates starting at the beginning of the 16th century, and the grape harvest dates again starting in the same time and continuing up to the present. These consist from two different sources. The older one part is once again from documentary stuff, institutional series. The new one are from phenological observations. I would like to stress that these three series are independent, so they correlate, as you will see, but they are different from different sources. The analysis is outlined here, so we do these three individual series, combine them in the PC1. PC1 explains 71% of the whole three series, so it's quite reasonable. And of course, they show some good correlation structures, so even if they are not dependent, they show the same signal. And we calibrated to instrumental data. Instrumental data were used in the form of mean Czech series for this period. Unfortunately, we had relatively small period for the calibration and verification. As for precipitation, here we used once again these indices, now saying something about the moisture regime or precipitation regime. and we combine them with the different kind of proxies from data from OAKS and from FIRS. So these tree-ring with indices that are presented here were standardized. It means the H trend was removed, and finally we use these series once again to combine with the documentary stuff. The same analysis, but a little bit weaker amount of common variability and also some weaker amount of explained variability as for this calibration period. But finally, we were able to produce these two final series. As you can see here, as for temperature, there are nicely expressed even some long-term variability with some warmer periods at the beginning and in the end, and colder periods here with the late Maunder minimum of solar activity. Precipitation showing no long-term trend with a very high interannual variability. Analyzing deeply this temperature series, here we tried to define this little ice age type of events using this series, and with these blue and red dots we identify the 30-year-long periods with the significant decrease or increase trend. So you can see that they accumulate in some parts of this reconstructed part of the series, and we define these blue columns and red columns as these little ice age type events. You can notice here, for instance, that this very relatively warm part at the beginning of the series was, from point of view of climatology, not so warm like recent climate, but dealing with the individual years, there were at least or even more warmer comparing to the present period. So it fits somehow with some other studies that confirm this conclusion that individual years, like for instance deeply discussed 1540, was maybe even warmer than present years like 2003. To find some less formal validation of our results, we collected some documentary stuff concerning this very warm period at the beginning of the series. As you can read here, these statements really speaking not about individual years, very warm climate in individual years, but on very warm individual, very warm climate, because as you can see here, planting some different species, it needs some time. So this is not the question of individual years, but the warm climate in general. Similarly, we can find some evidence for this cold period of climate. Here are some expressions, but I would like to stress that this period is to some extent influence of character of data which we used, because we used especially for temperature data from the anthropogenic archives, and this period just after the 30 Years' War was highly influenced of the situation, social situation, and for instance harvest dates were not driven not only phenology but also with some disturbances in the society. So finally, we try to compare our results in broader scale. Here we standardized at first and smoothed some existing reconstructions and projected these three periods on them. So you can see here quite nice coincidence of this cold period at the end of the 16th century, then also here in the late Maunder minimum, and not so big coincidence here. Of course, our reconstruction is related to the summer and spring temperatures, and most of you, of course, have an imagination of a little ice age with the winter temperatures. Here you can see the reconstruction of winter temperatures. This is not multi-proxy reconstruction, because for the winter temperatures we had only one source, these indices, and these indices show very similar variability of temperatures, but when we project these three periods found in the summer reconstruction, you see some differences. For instance, the first one in the end of the 16th century is a little bit shifted. Here is much earlier, very cold winters occurred. For instance, this year, 1565, from this famous painting, is the second from this series of very cold 4 winters in this part of the reconstruction. As for precipitation, due to much higher spatial heterogeneity of the series, it's quite hard to find some common features. At least I would like to stress this period that was not only very warm as I presented, but it was also very dry according to these reconstructions. So let's go to some summary. While the temperature reconstruction for summer and spring show very strong result, expressed here with the percentage of explained variability. For precipitation, the reconstruction, shorter season, shorter period, with some weaker result. Then, in temperature series, we were able to define two relatively warm periods at the beginning and in the end of the series. And we were able to find the coldest period that fits to this late Maunder minimum from 1673 to 1702. These well expressed little ice type events fits with these three parts of the reconstruction. When we compare the spring-summer temperatures with the winter, it means that there is no perfect coincidence. So winter temperature were lowest already in this final part of the 16th century. There is no clear signal on precipitation reconstruction, only just very high interannual variability, and comparing with Central European existing reconstructions, we found some coincidence and some very well-defined cold periods. So this is all. Thank you for listening.
If you could go back to the slide when you put this extremely hot year at the beginning of your record, please. Yeah, that one.
This one.
That you can see that you also have like the next year is like the coldest one in the record also. Did you find any kind of traces, because it's such a dramatic change that one should expect that you should have some kind of evidences of this high change in such a short time?
To tell the truth, I found the same pattern in some other reconstructions, especially for for precipitation derived from tree rings. But to tell the truth, I have no explanation at this moment for this behavior. This is not related just of the climate, of course. This is somehow related to the proxy used, but at this moment I don't have explanation.
So you trust more the hottest year than the coldest year?
Yes, yes, because this is 1540, and it was even in literature very deeply discussed, and there is some discrepancy between results that we can draw from the documentary stuff and also from the tree rings. So there is no coincidence. But we have some information from documentary that this year was cold, but that's all.
Debates on current and past climate change have resulted in the popularization of the topic among historians of various specialities, from traditional historians to environmental historians. Both historians and climatologists are interested in finding traces of climate influence on particular events in the past. Increasingly precise, more or less, environmental and climatological data are compared with the information from historical sources. Among the latter, very significant are weather observations recorded in narrative sources and early, often parascientific records of meteorological observations. Our project aims to completing studies to date with new data, data from mass sources of economic character, and we would like to create a ways of cooperation between economic historians and palynologists, climatologists, and broader sense sciences. And we focused on agricultural turning points in history in Polish agriculture. We tried to find results for 6 major things from establishing of the Polish state to the economic crisis of the 17th century. To illustrate our approach, I would like to present some remarks of our studies on a little ice age on the basis of Polish economic data, economic history data. In recent years, historians and climatologists have paid greater attention to the consequences of climate change. In Central and Eastern Europe, too. Jeffrey Parker, in his book on the 17th century global crisis, pointed out to the Polish-Lithuanian Commonwealth as example of a country affected dramatically by wars and the Little Ice Age. The peak of the crisis came in the middle of the 17th century during the so-called deluge, that is the war with Sweden. Parker wrote that Polish-Lithuanian Commonwealth encountered of the 4 horsemen of apocalypse: pestilence, war, famine, and death, with catastrophic consequences. Although Parker created a mesmerizing vision of the series of calamities that damaged Poland, he intermingled political, military, and climatic reasons for the crisis. From the point of view of historians, it is crucial that climatic data collected by climatologists and are correlated with historical events. Events, not then processes. New data for Polish lands of Central Europe, Eastern Europe, gathered by Polish scholars and eminent international research teams, correspond with general narrative of political, economic, and demographic crisis during the Little Ice Age. It is in our contention that the analysis of links between historical and climatic changes during the Little Ice Age can be advanced by including mass historical sources of economic character. For the purpose of this presentation, we have used data for late medieval and early modern Kingdom of Poland to the year 1650, prior to the Cossack, Russian, Swedish, and Transylvanian invasions. According to climatologists, these political military disasters coincided with the Little Ice Age, unfavorable to any human activity. However, historians are unanimous in calling these years the golden age in Polish history. So we are followed for after the Jan de Vries, great economic historians who wrote that influence of climatic change is real. Difficulty in detecting it may come from the fact that we have tended to look in the wrong places. There are no census records for Polish later Middle Ages and early modern period, but it's still possible to establish the population of the most important regions of the Kingdom of Poland. This is reconstruction in the higher graph of population trend. It can be done on the basis of surviving tax registers for 3 different chronological cross-sections. The first count is based on St. Peter's Pence registers from the years around 1340. The second uses land tax registers from the year around 1580, and the third is from the 17th century. These sources also allowed for the reconstruction of population development trends and pace of demographic growth. Lack of detailed sources makes it is impossible to establish the scale of cyclical demographic crises caused by recurring waves of epidemics. However, in our estimate of the pace of demographic growth, we have included potential losses. What is very important, unlike in other European regions, Polish sources do not confirm the presence of the first, the most devastating wave of the Black Death in the middle of the 14th century. At the end of the 13 Years' War in the middle of the 15th century and the incorporation of Royal Prussia with Gdańsk to Kingdom of Poland boosted commodity export from Poland to other European countries. The most important of exported goods was grain, especially rye, whose export increased markedly in the last decade of the 15th century to reach the maximum level in the 1619. Growth in grain export would not have been possible without territorial expansion of agricultural activity. In the 16th century, a true colonization and economic revolution took place in Poland. Data concerning taxed land show a real increase in the size of available arable land. It must, of course, be noted that the same sources inform about the process of sealing the taxation system and changes in rules governing the ownership of land, which may slightly distort, but does not appear to change the general picture of the growth in the size of arable land. Apart from the increasing amount of arable land in the hands of peasants, the second half of the 16th century also witnessed a dynamic development of manorial farms. It is estimated that about 60% of land was cultivated by peasants, whereas the remaining 40% was under the direct control of lords. The share of arable land in lords' hands must also have increased in the 16th century, but the scale of this increase is unknown because the land were not taxed. Foreign demand for Polish grain, growing internal demand, and the fact that Poland joined the international trade system resulted in an increase of grain prices. Among beneficiaries of this process were not only the gentry and other landowners, the clergy, the king, but also Polish peasants. And we've got some historians and environmental historians called it ecological revolution. Population growth, intensified colonization, and the development of manorial economy all had their impact on natural environment. A research group headed by Adam Izdebski uses pollen data as biological measure and indicator of human activity They collect data from some regions in Central Europe to Poland. Changes in pollen structure is analyzed. Pollenological samples reflect changes in vegetation in a given area and are indicative of the intensity of people's agricultural activity. Data from Polish lands reveal no significant crises in agricultural production during the Little Ice Age. In Lesser Poland, south part of Poland, palynological data from the period of German colonization at the turn of the Middle Ages and the early modern period era show an increase in the proportion of cereal pollen grains in pollen samples. The most notable growth is in the proportion of rye, which was one of the basic bread-making cereals. Slightly different graph for the Greater Poland shows relative stability and then a small drop in the agricultural output in the later Middle Ages. The extent of this decrease, however, does not indicate the occurrence of the population fall on that scale comparable with the Black Death or any deep economic crisis. What is clearly visible in the case of Greater Poland, although it's a significant rise in the proportion of cereal pollen at the beginning of the early modern era, which reflects surge in the production of cereals for export. And I think we've got some new possibilities for the research on climate change in historical perspective for Polish lands. And our project is meant to facilitate and promote cooperation between historians and environmentalists and climatologists. And from the point of view of economic historian, I can say that one of the most promising areas is the study of the impact of the Little Ice Age with the use of the historical analysis of grain yields. Although most data were collected in the past by Polish scholars with the aim of proving low efficiency of manorial economy rather than to illustrate any climatic changes, they can certainly be used in the analysis of various climatic processes. In the context of studies on Little Ice Age, it may be interesting, for example, to consider the question of decreasing grain yields in the 17th century. And another one of the aim of our project is to collect a big new database of the grain yields from Polish manors from the late 15th to the beginning of the 19th centuries. And we believe that this database will provide great opportunities for the study of climatic changes. We are also convinced that there is a great potential in the study of prices of agricultural products in the past, which can be correlated with climatic changes. Here are the oats prices in Krakow. Oats is the grain produced in local scale, not exported, so it is produced only for local people and sold in local markets. And if we see the tendency, we've got prices from year to year, and that the higher point is the first years of the 17th century. Some people can correlate it with the eruption of the volcanoes, but it is we can see it in the prices. We've got also prices for the every quarter of the year, so we can do the same for the collect data for the sixth biggest cities in Poland. So I think we've got some opportunities to develop cooperation between the climatologists and historians, economic historians. So, in my conclusion, I would like to underline that, of course, climatology and natural sciences contribute greatly to the advancement of historical studies, but we can, I think, data from the field of economic history may be particularly useful to climatologists. Data include population trends, agricultural produce prices, production volume, size of arable land, export and import, and grain yields. Thank you.
Thank you very much for this presentation, and I think it's very convincing, your construction of grain prices for that 16th, 17th century. It has been demonstrated by Bruce Campbell how well that corresponds to precipitation patterns. So this is, I think, it's a huge step forward. But my question is, for the earlier centuries, did you try to integrate narrative sources or charters, as sparse as the information may be on dearths, on famines, just to add a little more, all the information possible to your reconstruction?
Thank you. Yes, the prices in Krakow we've got from the end of the 14th century, but they are not the best, let's say. And for the former period, also we try to explore the different sources, historiographical sources, let's say. But the problem is that, which I saw also in the presentation during the conference, that when we put data from historical chronicles, annals, and something like this, from the point of view of climatology, we don't think how they were produced. So we can use the annals from Poland for the early modern period, but we should know that almost all Polish annals are written from German annals and Czech annals. So we can say we couldn't be sure if they show the situation of Polish lands or German lands or Western Europe or Southern Europe. So that's the problem. From historian, it couldn't be just mechanical transfer data from historical sources as information about climate.
What I want to do, I want to move continents and also move, I guess, timescales to an area where we've got generally a much shorter written record, and that's actually really the vast majority of Africa. And I want to talk on behalf of my colleagues from the UK and Norway about work from a larger project funded by the Leverhulme Trust, where we're looking at climate reconstruction for 3 regions. That's KwaZulu-Natal in South Africa, Madagascar, and what I'm going to talk about today, Malawi, all of which are within the zone of Southern Africa that's sensitive to El Nino. And what I want to try to do is, I suppose broadly the aims are to talk you through a rainfall reconstruction from the middle to the late 19th century, so we're coming much more recent in terms of timescales, but also start to explore some of the impacts of past El Nino events on patterns of rainfall variability. Reason we're doing this in terms of rationale, if you look at this map here from Sharon Nicholson's work, what she's showing here are locations in Africa that have at least 1 or more year of meteorological data during the 19th century. And you can see that there's very, very sparse coverage. We do have some records in Malawi, but not a great deal, and they're really all from the very, very late 1890s. So I suppose part of our goal here is to try to expand the weather record for this particular part of Africa. And I'll say a bit later on, it's actually quite an important sensitive area in terms of climate. So that's another goal that I'll come on to in a moment. To give you a bit of climatic context, so where we are, we're in the Southern African summer rainfall zone. We're south of the equator. And other work by Nicholson identifies that Malawi has 4 distinct homogeneous rainfall zones. So it's a very strongly seasonal climate, which is fantastic for doing documentary-based reconstructions because it means people are waiting for the rainy season. So when it arrives, they write about it. They're very much dependent on it for their livelihoods. So we get very, very good written records about rainfall. But these 4 zones, Nicholson discriminates them. Hopefully you can see over on the left-hand side. They don't look that different, actually, but they are statistically different in the sense that what you pick out in the north is a distinct break season in February. In the south, you pick out slightly different start and end dates of the rainy season and slightly different magnitudes of rainfall. So there is these 4 homogeneous rainfall zones. The early part of the rainy season tends to be dominated by more tropical rainfall influences. So we've got the movement of the tropical easterly jet, which brings rain belts, which brings rain during December to February. And then as that migrates back northwards, as we move into the southern hemisphere winter, we start to see a greater extratropical influence. So what we're picking up is a mixed signal in Malawi. There's not much correlation between variability in these 2 different chunks of the season. I think the interesting thing, though, is that what you often get in the record is opposition between the rainfall in the north and the south, and a large proportion of that is due to the impacts of El Nino. So if you look at the sort of your classic impacts of El Nino map here, Malawi sits right on a hinge line, if you want to think of it that way, between an area of southern Africa that typically has drought in years following El Nino events, and Eastern Africa, which typically has wetter periods. And I'll talk a bit later on about that, about whether we can pick up this sort of hinge line within our reconstructions. Okay, so that's, I suppose, really a bit of context. In terms of sources, we're fortunate that there are quite a number of archives which contain materials relating to Malawi and Central Southern Africa more broadly. And we've looked, I think, at pretty much all of the main collections. Much of our work's focused in the UK, also in Malawi and in South Africa. We've mainly focused on missionary collections, so a really important component of the information for Malawi comes from very, very early missions, particularly the University's mission to Central Africa up the top here, and then later Scottish missions, which worked right the way along, particularly along Lake Malawi. But we also pick up records from colonial administration, and also, as we get towards the end of the 19th century, more in the way of newspapers and so on. So we have quite a good diversity of different types of sources. Now, what we've done with these sources, just to briefly explain, those of you who don't do this sort of climate reconstruction, we've used a fairly standard historical climatology methodology in which we read materials, we record any quotes about climate and environment verbatim along with their context. We've got a database which we code these quotes into. Then we collate our quotes by rain year, so we encompass the hydrological year from July to June. And then what we're able to do is to start breaking down these records into seasonal blocks. So we look at July, August, September, October, November, December, and so on. And in this case, my colleague Georgina Enfield and I worked through those quotes together, attempting to classify each season into one of 5 categories here, from very wet through to very dry. And we also assign a qualitative confidence rating for each year from 1 to 3, according to what we consider the strength of our classification is. So what we're looking for a +2 would be accounts of floods that cause major damage. People are talking about them being record-breaking, those sorts of things. Droughts might be ones that are associated with death, cattle dying off, problems of food shortages, and so on. Ones in the middle are a bit more relative. What we then do for an individual year, if we wanted to get the annual classification, what we do is very simply a sort of a tallying process whereby we add up the scores for each season. We double weight the middle seasons of the year. They're the ones that have the most rain, and we come up with a classification. And in the event of a score coming out at 0.5, we place more emphasis on the January to March value, because that would be the one that has the greatest rainfall. So we end up with a chronology. So on to sort of, I suppose we're moving between methods and results here now. What we end up with is actually a very good geographical spread of information. So we have data from sites from right up in the north of Lake Malawi right down to the Zambezi River. Unfortunately, none of those fall in zone 2 of Nicholson's climate zones. So we're only able to reconstruct for zones 1, 3 and 4, but we have pretty good resolution information for those 3 zones. And if I just show this plot, I know that those people who work on quantitative subjects like to see a plot of how many data points you've got. I don't hold a great deal of sway on this because actually 3 or 4 really good qualitative descriptions that are doing some comparative analyses are much better than, for example, weather diaries. And what we have here is some years, particularly in the 1890s, where we've got more than 200 quotations for a year, but a lot of them are from daily weather diaries, and they don't give you necessarily a huge picture of seasonal or interannual change. But we're looking at, certainly for the period early in the record, relatively small numbers of quotes, but quite often rich in detail. By the time we get past the 1870s, this is really when the first missionaries started to arrive. So this block of records dates back to when David Livingstone and his expedition went up the Zambezi River and started exploring the southern part of Lake Malawi. But once we get past here, we're looking at maybe 30 quotes a year on which to base our reconstructions. Okay, on to some results then. So you can see we're looking at a much shorter record. We're really only looking at maybe 40 years, and for our all 3 zones, we're only looking at maybe 25 years of data. But what we can start to pick up is, certainly in these early records from when Livingstone and his expedition first went up the Zambezi, are relatively dry conditions. So we find a particularly wet year around about 1860, but we find a very, very dry period in the early 1860s. That's in zone 4, so that's in the south of our region. When we get into the 1870s onwards, this is really, as I say, when missionary activity started to spread around Malawi, and there was a fairly rapid proliferation of mission stations and lots of written material starting to emerge from the region. And we start to pick out, again, patterns of climate variability here. You can start to see some droughts, you can start to see some wetter periods emerging here. And if I superimpose some bars just to sort of highlight those, you can start to see probably 5 reasonably well-defined drought episodes, these ones in the 1850s and 1860s, late 1870s, late 1880s, and then in the mid, not quite so strong and clear here, but the mid 1890s. We've started to look at, so also say you pick out wet periods, and you notice the 1890s is also relatively wet. We've started to try to calibrate these data. This is very much still work in progress. We don't have masses of instrumental data from which to do this, but what I've put on here is just the available rainfall data for 2 locations in the south, in zone 4, Blantyre and Zomba, where we have reasonable runs of unbroken rainfall data, and you can see hopefully here what I've done is I've just presented the mean rainfall values, and if you compare these against zone 4, you can see there's actually a pretty good match here, completely independently. So the first record here, we're picking out drought in the south, and we've got well below average rainfall. I should say that's the 1890s average, that's the whole record average. So that's running right the way through to 1992. So we can see actually that the 1890s were a bit wetter than the longer term mean. But what we're seeing here is a very clear indication of drought, and actually wet years, when we're identifying wet years, which is quite reassuring. The only one that doesn't work brilliantly is this one in here, which is, I suppose it's not bad, it's a normal year. We pick out the drought very effectively at the end. So I think we've got some quite good, I wouldn't call it calibration, but at least some independent verification that our classification is working reasonably well. We can start then looking at things like El Nino patterns, at least at a qualitative level. Now, what I've put on here is the record from Gergis and Fowler of El Ninos, and I've only shown the moderate, strong and very strong events across the top. There's also a number of weak ones. And I think there's a few observations we can make about this. I think the first thing to say is that normally not all droughts are associated with El Nino events. That's the same we find from the 20th century. But there are some instances where we see a very clear signal and a very clear response to El Nino. Quite an interesting one, if we look right at the end of the record here, is the very strong El Nino event 1899. And you pick out almost a perfect pattern from Malawi where we get drought in the south and wetter than average conditions in the north. But there are some El Nino events where we see consistent drought, and there are some El Nino events where we see consistent wetter conditions. And what we're thinking is going on here is that you've got effectively an expansion of either the drought zone associated with the El Nino event, so that drought area which would have covered southern Africa, or the southern part of southern Africa, or you've got an expansion of the eastern African wet zone. So it may well be that through this we can start to constrain the spatial events, the spatial impacts, I guess, of these different El Nino episodes. We need to do a bit more looking into that, and particularly to look at the seasonality of the rainfall to see whether we're looking at early rainy season conditions or later rainy season conditions. So I think that there's some potentially quite interesting patterns that will start to emerge from this. Where it starts to get very, I think, more interesting though is when we start to compare this to more regional patterns. And I'll just show a last couple of slides and then wrap up. What we start seeing, actually this is quite interesting, I'll show a sort of a comparative slide in a moment, but I'll just put a couple of quotes in here because I know that I think it's quite useful to see how you can get these classifications from the actual documentary data. What we start to see is, in the 1860s, is a regionally wide drought episode. This is just a couple of quotes from the south of Malawi, talking about the conditions during the 1860s and describing, I won't read them, but describing particularly people dying off. The second quote here, which is from a newspaper in South Africa, reporting on broader conditions, describing dead bodies found amongst the grass and dead bodies being seen floating down the river. This was an absolutely catastrophic drought event in Malawi. Another example here, this is from a very wet rainy season, gives you an idea of the sort of things that people say, but in this particular one, this is an interesting one because this is when Malawi was wet, but as I'll show in a second, other parts of southern Africa were experiencing drier conditions. But here you're looking at accounts, for example, in the newspaper The Central African Planter, talking about record rainfall in this season, and then at the bottom here talking about massive improvements in the navigability of the river, which was absolutely critical for transporting materials into and out of Lake Malawi. So if we have a quick look at some regional comparisons, and then I'll wrap up. What we're fortunate now that we've got a growing number of records that are producing this sort of annually resolved data for Southern Africa. So there's a series of documentary-based reconstructions. There's also a tree ring-based reconstruction for Zimbabwe, and we can now start to add our Malawi data to that series. And what I've put on the next slide, and this is really the final slide, is a horrific multicoloured bar chart that looks remarkably like a DNA sequencing thing. And I apologise, one of my colleagues said to me, what about people who are colourblind in the audience? So if you are, I apologise between my reds and my greens. You're probably looking at a grey diagram here. But what I've tried to put on here is the records from Malawi, so this is our new data series, and then a whole series of other annually resolved records. I've cut out, I should say, these ones go back to the early 19th century. I've only done the portion that overlaps. But what you can start to see, hopefully, when you get your eye in, are some regional patterns of drought. And I'll just bring in a few highlights here. So if we just put some of the, if it'll work, if we put some of the droughts in here, you can start to see some really quite clear. The 1860s drought was by far the most catastrophic drought of the 19th century, and we know that from multi-proxy reconstructions, and we know that from other records, and it also seems to have affected Malawi in a very bad way. And we also pick out droughts in the 1870s that seem to be probably subcontinental in scale. I should add we don't have much from the west of the subcontinent to go on. And we start to pick out some other droughts maybe in the 1880s. There are some, like the ones in the 1890s, that didn't seem to affect Malawi. They affected Zimbabwe, but we seem to have in those areas a much stronger tropical influence of rainfall perhaps compared to areas to the south. You can also add on wetter periods as well. If I just put a few on there, you can start to see, you know, the 1890s in Malawi were pretty unusual actually. You can see a wet phase here, but the mid-1890s, and that's also the area that we've got the most data for, so it's one of the years that we're most confident for, have very, very different signals. And what we're wanting to do now, and I'm very much at the end of what I want to say, what we're looking at now, as I said, is trying to see if there's any difference in the seasonal variability. Are we picking up dominance of early rains or later rains that might give us clues as to whether we're looking at a predominantly tropical influence or a more extratropical influence? And also, how do these data sets now relate to things like 20th century reanalysis data or other records that might start to give us some clues as to what's driving this variability? So I suppose what I've presented here is really sort of our results. We're still very much at the stage where we're now starting to look at the why are these different patterns happening. So I'll conclude at that point. So what I've tried to do is I've tried to show, okay, a relatively short record, but what we appear to be picking out in Malawi is certainly countrywide droughts and some very widespread wetter phases from documentary series. Some correlation with El Nino records, but not necessarily very clearly. I think the most interesting thing from this, though, is that there's quite a lot of potential for now starting to pin down from terrestrial evidence the geographical impact of individual El Nino events upon rainfall patterns. So I should leave it at that. Okay, thank you.
So yeah, my talk is reconstructing ENSO using ship logbook data, and this looks primarily at the period 1815 to 1854. This is research part of my PhD, which is funded by the University of Sheffield, and I've written it up with my supervisors and co-authors, Julie Jones and Grant Bigg. So yeah, the climatic focus of my research is ENSO, which is a phenomenon within the equatorial Pacific but has global implications. So it's quite a wide socio-economic impacts when there are strong ENSO events, such as El Nino or La Nina. This is the Southern Oscillation Index, which is one of the main instrumental records of ENSO. And it extends back quite far, actually, till 1876 in this form, which is the pressure difference from Tahiti and Darwin. So yeah, I'm going to try and reconstruct ENSO prior to this instrumental period in order to have a look at the longer scale changes in ENSO and to try and use more direct weather observations rather than proxy records. And this has been recently published in Climate Dynamics and builds upon work from Jones and Salmon in 2005, who used similar data source but had less data available at the time and were limited by the data at that time. So yeah, there are lots of ways you can look at ENSO in the past beyond the instrumental record. There's lots of documentary records out there, proxy archives, and also through climate models. I've looked at historical logbooks. So this is just an example page from a logbook. So they are written every day on board the ships and recorded by senior officers for navigation and safety purposes. So they're quite important documents on the ship. And they included a range of weather observations, but not all weather observations were taken at each day. And this is just the type of ship that they were taken on. So yeah, the meteorological observations is what we're interested in. There's a range of observations available. So there's wind force, wind direction, temperature, pressure, and also just comments on the state of the weather and the sea in general. We've kind of focused on the wind observations because they're more consistent through time in the way they were written down and the practice. And the temperature and pressure observations are less commonly available earlier on in the record and are more like have a few more errors based on the different types of measurements that they were taken. So the wind force, this was the period that we're looking at. Some of the period is before the introduction of the Beaufort scale. So there's just general wind force terms that were used. So one of the digitization projects, which was called the Climatological Database of the World's Oceans, correlated all the different wind force terms from the different ships. So they used English, Spanish, Dutch, and French ships and found any words that related to wind force within the logbooks. From this, they put them all together and classified them into Beaufort force equivalents. And then from that, you can convert them into meters per second squared. So you can use them kind of as modern day wind force terms. And wind direction was measured quite commonly using the 32-point compass and just with the direction the wind is coming from. So yeah, these are wind observations. They were, after digitization, there were a few studies that did cross-checks between ships that were traveling in convoy. So often ships traveled in convoy with the same nationality. So you could compare the different wind force terms used on the same day within ships that were in the same region to see if they matched well. And these studies found that there was a good match between those of the same nationality within the same regions. So we have quite good confidence in the wind force terms. The wind force terms were also passed down through generations of sailors, so they weren't found to change too much over the time period that we're looking at. And although the Beaufort force scale was introduced after the start of our logbook reconstruction, a lot of these terms are fairly similar. So the logbook data that we use two digitized databases, so we didn't do any digitization ourselves. We use these which are available online. And this was, the first project was the Climatological Database of the World's Oceans. So this expands from 1662 to 1854 and includes British, Spanish, Dutch and French observations, as it was an EU joint funded project. Most of the observations from this period are from 1750 onwards, though. And then later on, more recently digitised, is the English East India Company data, which covers kind of the middle portion of this 100-year period. And these were carried out digitisations in the UK. The figure shows the number of observations from the logbooks from 1750 to 1854 globally. And the grey just shows any logbook data entry regardless of the meteorological variables available. And then the black shows ones which have both wind force and wind direction, as well as correct latitude, longitude, and temporal information. So you can see in the middle portion of the 100-year period, there is a period with logbooks which don't have all of the wind information, and this matches up kind of with the English East India Company data, which did digitise a lot of wind data, but they focus primarily on pressure and temperature. So there is a bit of a gap between the data there. And this shows the spatial distribution of that data. So this is the data with the wind observations. And you can see quite clearly they follow historic shipping routes. So from Europe across the Atlantic Ocean down South Africa, and then across to the maritime continent in India, where they did a lot of trade during that time. For us, we were looking at ENSO, so we were quite disappointed by the lack of observations in the Pacific, obviously. But as it's a phenomenon with strong teleconnections, we just use different regions where there is enough data and the strong teleconnections. So the methods that we use statistical-based methods of reconstruction, so looking at modern day data that we have, assessing the statistical relationship in the modern day, and then applying it to the historical wind data. So we look at the DGF season, as this is where the strongest peak of ENSO is, and we found the strongest correlations within the regions that we looked at. So yeah, this is the seasonal SOI, so just the Southern Oscillation Index, correlated with era interim zonal wind. And we calculate the zonal wind using the wind direction and wind force observations from the logbooks as well. So yeah, this plot just shows the correlation over the modern period using the era interim reanalysis. And you can see that there's a lot of different areas across the globe where there is a strong correlation between ENSO and zonal wind. And then you can see the black dots, which indicate the historical observations, so the wind observations that were available at that time. And what we had to do is match up regions with good data availability in the historical period with good strong correlations in the modern period. We use quite a coarse resolution, so it's 7.5 by 8 degree grid boxes, but this is commonly used within logbook studies as to enable enough data availability in the logbooks grid boxes themselves. Oh, yeah. And so the black grid boxes are highlighted. So there's 9 grid boxes that we've chosen, which were based on our criteria. There was 5 in the Indian Ocean, 3 around South Africa, and 1 in the Atlantic Ocean. And these are mainly chosen because of the data availability and the correlations in these regions. So using these 9 predictor grid boxes, we used the era interim reanalysis to reconstruct a modern day SOI, and then compared it to the instrumental SOI to see how well our method and our grid boxes would match up with the instrumental record. And we found a really good correlation, so we used 2 different methods, principal component regression and composite plus scale. They're 2 similar reconstruction methods used commonly in reconstructions of logbooks and proxy data. And they found a good agreement, so 0.89 and 0.87 correlation with the reconstructions in the modern period and the instrumental SOI. And we also used a reduction of error skill scores, which came out quite high as well, which shows good agreement with our reconstruction. So therefore, we used these methods and applied them to the historical wind data in the past. So here are our reconstructions. So you can see that they go from 1815 to 1854. We originally looked back to 1750, but found there wasn't enough data in the logbook grid boxes that we chosen. So we go from 1815 onwards. And there are 4 different reconstructions based on slightly differences in the methodologies that we used. So there's 2 from principal component regression and 2 from composite plus scale. And the bottom one's been adjusted slightly due to a bias we found within the wind force data. So now I just want to compare these to some other records that are available at the time for ENSO, and I'm just going to compare the last one, so CPSB. So we found another SOI reconstruction, which was based on direct observations of the weather, and compared that to our logbook reconstruction. So this Jakarta rain day record from Conan et al. In 1998 was based on a record from the head of road maintenance in Jakarta. And the road maintenance, their job was to water the roads on days when it didn't rain. So they wrote down every day if it rained or not, and if they had to go out and water the roads. And this was a daily record from 1829 to 1850, so it's quite a long period which daily records are available from. And then, so the rain day data averaged over the month is then correlated with pressure from Jakarta, and from that they could reconstruct ENSO based on the pressure difference from Jakarta and Tahiti, because the Tahiti pressure goes back longer than the Darwin does. They produced a SOI, and we compared it to ours, and it came up with a correlation of 0.55, which we think is relatively good at this time because they're it's quite general good agreement, and it's quite a short period to compare over, but it's still fairly strong agreement. And then we compared it to more indirect records of ENSO. So there's been a large number of multi-proxy reconstructions of ENSO over the past few decades, and we just selected a few that covered our time period and were at an annual resolution. They look at different ENSO indexes, so some of them look at the DGF SOI, is what we focused on, but there's also ones which look at Nino surface temperatures and the Unified Proxy Index. And these use a range of proxy records from tree rings, corals, ice cores, speleophans and sediment, and from different regions around the globe, so they're quite big proxy networks, and using different methodologies, they've produced different ENSO indices. So this is a plot showing a comparison between these ENSO proxies, proxy reconstructions, and our reconstruction, which is in black, over the entire historical period that we reconstructed over. There's a generally good agreement, but it's kind of a bit scattered, a lot kind of not as obvious as the agreement with the Jakarta record. And it ranged from the correlation between 0.42 and 0.19 with the individual multi-proxy reconstructions and our logbook reconstruction, 5 of which were significant correlations. And then from this, we wanted to look at more just ENSO events in a more event-based level. So we converted these time series into an individual ENSO events. So here, the negative events are El Nino and the positive events are La Nina based on SOI. And the grey bars indicate a logbook one from our reconstruction. Yeah. And the colours show ones from the multi-proxy reconstructions. So you can see that there are some areas where there is agreement. So in the early record, there's a La Nina event, which occurs over two years in ours and 3 years in some of the other reconstructions. And then in the late 1830s, there's also an El Nino event, which is caused in a couple of the reconstructions as well. But you can see that there is not really great agreement over the whole record, and a lot of events are picked up in 1 or 2 records, but not in all of them. And some of our logbook events are not found in any of the other records. So to look into this a bit more, you need to look at the signal from the individual ENSO events and from the individual proxies, and see kind of what signal is coming through from all of the different proxies. So yeah, just to conclude, I wanted to say that we think it would be really important to try and extend this instrumental record back further into the past, using direct observations of the weather to then reconstruct an SOI index. And it's been shown that the logbook data that we have available digitized at the moment is useful for that and can be used to produce a reconstruction that does compare well with the Jakarta rain-based record. But yeah, there's still a lot of logbook data left to be digitized. Over 90% of the European logbook data are still in the archives, ready to be digitized. And digitization of these would improve the robustness of these reconstructions and also extend it further back in time, hopefully to about 1750 as well. Thanks.
Well, I'm not the expected speaker, so I apologize for this. I'm just the second author of this presentation. And the end of this presentation is to show you the possibilities of some ongoing work using documentary sources in South America. The problem in South America is very similar to that we have just seen in Africa. It's a region of the world where you have very little proxies and very little observations. So, which implies that in order for reconstruction, you have more problems than in other areas of the world. What you can see here in this picture is this is a paper of 2012, where you can see the distribution of natural proxies along South America. And what you can see is that they are mostly concentrated, these are natural proxies mostly, and they are concentrated along the Andes Cordillera. And basically they are tree rings and some evidences of ice cores and this type of natural proxies. So it implies that basically most of the continent is empty. Okay? So,
if you click outside the menu, it'll disappear, and then you can use the pointer again.
Okay. Okay, that's it. Okay, this is a review. Sorry, this is because I just clicked down. Okay, no, it's okay. So this is with more detail the location of sources where you can find evidences from documentary evidences that they cover again mostly associated to the Cordillera, and then we have some records about here in these plains. So basically, looking at high resolution reconstruction in South America, we have this problem of lack of proxies, lack of documentary records, and also you also have a problem is that there are not also much instrumental series. So the overlapping between the instrumental series and the proxies is really a problem because both types of series are short. And this another problem is the continuity in the case of documentary sources, the continuity of the sources. Because paradoxically, you can find in most of the archives, you will find continuous records until the beginning of the 19th century. And then suddenly you will find nothing. And this is because the establishment of the Republic period in all these countries was very abrupt with a lot of wars and incidents, so there wasn't a continuity of the administrative structures, and also many documents were lost due to the wars. So paradoxically, you might have more information of the colonial period than in the more recent 9th century with the new republics. So what I will show you today is three types of evidences. All this is work in progress that we are exploring in different areas of this region. The first thing is an exercise of early instrumental data. This is a database that we are assembling, which we call EMERLAG, for early meteorological records for Latin American and the Caribbean. This is being assembled by a group of people of different countries looking at local archives, but also our resources which are available in the web. We have been able to ensemble so far more than 300,000 observations. They have been retrieved from documents like this. This is a paper from La Habana, starting 1980 something. But most of the records cover just the 19th century. Okay, you can also find some things different. This is a barometric record in Puerto Rico. Okay, so you have a variety of documents, a variety of sources, some of them in local archives, some of them web-based, but most of them must be digitized. Which is the problem here? The problem here is that most of the records are for source series. So which implies that the longer record that we have found is in Cuba, which is 20 years of continuous observations, daily observations for this period. And the earliest observation is for Lima, which starts at the end of the 18th century. So some of the series can be used just to establish some kind of climatologies, but for the rest, I would say that more of them will be interested for the analysis of extremes. Some of them, for example, have been used to analyze the impact of the lucky eruption in the area. The other example is something which we think that perhaps has more possibilities. It's an example of a meteorological, we call it a weather diary, which was kept by Felipe Zúñiga Ontiveros in Mexico, in Mexico City, during the end of the 18th century. We call it a weather diary, but it wasn't really a weather diary. It was an astronomical diary, okay? He was interested in astronomical observations, and then, as in many cases in Europe, the development of the meteorological observation was associated to the astronomical observations because they had to check the weather status for that day. So we have found, in this case, in the Spanish National Library, weather diary 1775-1786. It means 11 years of daily observations, continuous, not only in time, but also in the people who record that. And this is how the document looks like. In this page, you find the astronomical observations, and in this other part, you find the meteorological observations, but also some kind of, I will say, societal information. For instance, here, it was that it is the day that Pius VI was appointed Pope. Okay, so you find a lot of information. But looking at what type of meteorological information you can have, this is the common structure for the whole period. I mean, and here it says fair weather and cold, and some clouds in the afternoon. Fair and cold, and wind in the afternoon. Okay. So what we have made is just to extract all this information. I will show you mostly what we have done with precipitation, because with temperature, due to the region of the world where we are, the variability of temperature is more difficult to capture, but except for those years which were, you can see that this is rainfall, and rainfall means here the frequency of precipitation. Also, again, in this area, the frequency of precipitation is highly correlated with the intensity of precipitation, because precipitation here is mostly of convective origin, and so the frequency of precipitation is highly correlated to the amount of precipitation. But the end of this period, these were two disastrous years in Mexico with high famines, because the loss of the harvest and crops because of very cold episodes and frost and all this. So you can get a record of interannual variability of precipitation, also storminess, and for instance, streams like hail. But looking at, okay, how can you trust this? What we have made is a comparison of the seasonal cycle of precipitation in terms of the monthly frequency of rainy days. And you can see here in blue is the record of this diary, and in green is the precipitation recorded in the instrumental period. You can see that basically there are not relevant differences, except that in the peak of the rainy season, perhaps the frequency of precipitation is overestimated. What we have also made, just trying to go a little bit deeper, is to look for analogues of those of this precipitation situation. And what we have seen is, okay, we have identified the patterns of the driest, which are those in red, and the wettest years, okay? And then we have gone to the 20th century year 20th century reanalysis, and we have looked for analogues. To have an idea of what type of circulation was associated to these dry and wet years. So these were the analogues that we got for the dry years, and those were the analogues for the wet years. What we got was we will have 3 analogues for the wet, and what we saw was a clear ensocygnal, even when the ensocygnal in Mexico is not robust. It depends on the events, so you cannot use really the precipitation in Mexico as a real proxy of ENSO. And the other relevant thing was that you can find here is an increase of the Caribbean low-level jet, okay, which should be the other driver. The idea is that this intense low-level jet inhibits convection in the area and could be an explanation of this dryness of these analogues. In the case of the wet years, the things are not so clear, and what we find basically is an intense PDO, and again, in this case, a weakening of the low-level jet. This is the more relevant mechanisms associated to these years using these analogues for the reanalysis. And the third example that I wanted to show you, we have seen from early instrumental records, then we have seen direct meteorological observations, now proxies. The proxy that I want to show you is proxy from rogation ceremonies in Quito. Now we move a little bit to the south, we move to Quito. As you know, rogation ceremonies records have been used as proxy, essentially, of precipitation in many Catholic countries, especially southern countries, here in Spain, in Italy, and also in Portugal. What we have made in this case was, from the one hand, this is, we have recovered the longest observational series of precipitation of Ecuador. This is unpublished, by the way, yet. And we have computed the SPI drought index at 3 different time scales. And we have been able to identify these periods of wet and dry episodes. Okay, so we have an idea of which is the behavior of a drought during the instrumental period. And then we move to this type of records when people just didn't know how to claim for rain or for fair weather, because they celebrated 2 types of rogations. Pro-pluvias, when they needed rain, and pro-serenitate, when they needed that the rain should stop, because the excessive rain should damage the crops and even should impede the harvesting. Okay, so we have these 2 types of records which are sensitive to as you will be able to see, to different weather and climate conditions. So what we have made is we have from the chapter apps kept in Quito, we have collected the series of rogations in Quito, for the period, let's say, starting the beginning of the 17th century to the beginning of the 19th century. We have a gap here. Okay, this is what we got. The first thing, of course, which is the meaning of these rogations, which is to which type of drought are they associated to. So what we computed was the monthly distribution of the frequency of the rogations. You can see here for the pro-serenitate, and then here for the pro-pluvia. In this case, asking to stop rain. In this case, asking for rain. And what you can see here is the seasonal cycle of precipitation. Okay, so what you can see is that, of course, the pro-serenitate rogations are indicator of wet summers, because this was the type of collection, the crops, So what they required was a dry weather. So if in July, August, they had excessive rain, they went to, they organized this Pro Serenitate, okay? Again, when they needed water, well, in this, basically, January, February is the month when, if in this case there was water scarcity, they organized these pro-pluvia rogations, okay? So I move on. This is what you find, and then look at this concentration of drought. Okay, so this is interesting. See, but what we said, okay, how does it compare with the present climate? So what we made was a surrogate rogation index, comparing the SPI with the rogation, and we said, okay, the more negative SPI 3-man values, because we have seen that they were associated to agricultural drought, and this is the more appropriate scale. We think that they are associated to the more negative to pro-pluvia, and those associated to the more positive to pro-serenitate. Okay? And the other thing that we imposed was that the frequency of rogations, the average frequency, was similar. This, of course, doesn't allow you to compare the absolute frequency during the both periods, but what it allows you is to compare the interannual distribution of droughts, okay? That this is what we interested us, okay? So, and what we found interesting, sorry, this is just, what we found is this. This is the instrumental record, and this is our historical record. And what you can see is such a different distribution, interannual distribution of droughts, okay? And you can see that this period here probably doesn't have any precedent, is unprecedented in the whole record. In fact, we have a record here that at the end they said we celebrate the jubileus to solve the calamities due to the lack of grain and bastiments for more than 14 years. 14 years of drought, okay? So, just to conclude, just to encourage your interest that even in this area, for some of you can be remote, there are still a lot of possibilities looking at documentary sources. There is still a lot of collections of early instrumental data. For instance, most of the collections of the official weather services has not been digitized. So many of the national weather services have hundreds of meters in themselves of undigitized weather observations. The investigation about this type of weather diaries is still very in the earliest stages, and there are more places when you can find records similar to those that I have shown you as for the rogation ceremonies. That's all. Thank you very much.
Ricardo, thank you very much for a very nice presentation. I have just a question concerning of these rogation ceremonies. Also, is it fully comparable with Spain? Also, for example, have been there also this decrease from 1 to 5, as is known from Spain, and how complete these data are also, because there have been some periods where it looked like there would be lack of information also. Would you like to comment it a little?
Yeah, let's see. The record, as you can see here, is that these are the main gaps that we have. But for the rest, since this has been taken for a compilation mostly based on the chapter ads, and then you can see that it interrupts in 1822, when mostly independence and the Republic started, and then everything collapsed. And this is why we didn't have, because after this, there's a model record for rogations. But we think this is not comparable. So that because the society changes, the procedure changes, and then what we have seen is that there are no changes nor in the frequency nor in the patterns along this record. But after this, that one had the temptation of extending this to present because there are still some rogations. We think that it is not comparable because there was a lot of instability, the role of the church changed, and all these things.